Okay, we're going to start up again. We're going to talk about channel routing, and actually we're going to talk about several topics. What's that? We're recording. I'm recording. Okay. So I want to talk about how water gets from the overland flow plane into your channels. And there are three conditions you can have. One condition you can have, and this is only if you're running groundwater. One condition you can have is your channel thalweg could be higher than your so your channel thalweg can be higher than both your overland flow elevations, and it can also be higher than your groundwater table. And if that's the case, then no water is going to go from your overland flow into your channel. There's no way for water to get into that. And so your model is probably not going to be correct. The other condition you could have is your channel thalweg will be higher than your groundwater, but lower than the water in your overland flow. And if that's the case, then water will go into your channel from your overland flow, but not from the groundwater elevations. If your channel water depth is lower than both your groundwater elevations and also your overland flow, then and that's this case over here, so your water depth is lower than both, then you're going to get water flowing in from both the groundwater and the overland flow. And so those are the three conditions you can have. That's how stream flow is generated. And I want to kill that fly. It keeps biting. Does it bite people? Do the flies bite? No. I feel like it's biting. Okay. So in GSSHA, when you were setting up your, remember when you went through the workshop, you selected several stream arcs, and along those stream arcs you changed the elevation of you got rid of any adverse slopes. And that's basically defining your stream network. So you define your 1D hydraulic model using that method. And it's a good idea to get rid of adverse slopes, but like we saw, you can actually have adverse slopes, and GSSHA seems to run. A lot of times it will not run if you have too many adverse slopes. So you want to get rid of them if you want. And the stream flow in GSSHA is just a 1D network of links, which are reaches or arcs containing several nodes, the nodes are cells or arc segments. So in GSSHA, the terminology in GSSHA, there are links and then there are nodes. And a link in GSSHA is an arc in WMS. It's a stream arc in WMS. A node is a segment along an arc. So it's between two vertices on an arc, or between a vertex and a node on an arc. Each segment of an arc along the polyline that represents the arc is a node. We call that a node in GSSHA. So GSSHA, the terminology in GSSHA for arcs is a link. The terminology for segments along the arc those are called nodes. And GSSHA uses one-dimensional stream routing, and this is just Manning's equation. It's kind of a form of Manning's equation. So Manning's equation is that the velocity equals 1 over n r to the 2/3 s to the 1/2, right? That's Manning's equation. And N is the Manning's roughness value. R is the hydraulic radius. S is the slope. In this case, we're multiplying this all by A, the area of the channel, and that'll give us the flow rate. So we're just using Manning's equation, and we're doing an energy. It's kind of like HEC-RAS, where you start at the downstream end and use the energy equation to get the depth at each location in your model. So the stream alignment and spacing is independent of the overland grid. You can have streams wherever you want as long as it's inside of your grid. You don't have to have you don't have to align your streams to your grid. Don't worry about that. There are a couple of types of streams that you can use in GSHA. One type is called trapezoidal, just trapezoidal stream cross sections. The other type is breakpoint. And breakpoint cross sections are where they're user-defined cross sections. So just like you can have cross sections in HEC-RAS, you can also have cross sections in GSHA. And you define your hydraulic structures like detention basins, weirs, culverts, rating curves, and discharges, scheduled discharges, rule curves. So you define these hydraulic structures at nodes that are attached to streams in your 1D hydraulic model. And all those different hydraulic structure types are supported in GSHA. So for 1D channel routing, for channel flow, 1D hydraulic model, you need cross-section information, you need your Thalweg elevation information, and then you need Manning's roughness for each of those streams. And the node size, so when you redistribute the streams, when you create these streams, there's a number that you enter for the redistribution size. That number should be about the same as your cell size. So 0.5 times your cell size to 1.5 times your cell size should be what that number is. And just so you can, and it's a good idea to capture the stream, how the stream flows in your watershed. That's the sinuosity of your streams. So to set up your stream routing in GSHA, we've already done this, but you just set up your GSHA model and you need to smooth your streams. And the hydraulic modeling wizard will help you do that. If you have a user-defined cross-section like this, you can just define your stationing and your Z values, so station and Z values along the user-defined cross-section, and then that can be used in GSHA. You can also just define a trapezoidal channel for your stream. You have to redistribute the vertices, so that's just selecting your stream segments and this window. So in this window you define a spacing that is about the same as your grid cell size spacing. You can smooth your stream Thalweg locations. And then one important thing you have to turn on is you have to turn on the diffusive wave option in the job control dialog to turn on your 1D hydraulic model. If this no routing option is selected, then you don't have a hydraulic model defined. You're just going to be running overland flow in GSHA. So I have to select the diffusive wave option in here. Then I can output my channel depth and channel flow rates. And then I can run my simulation. And like I mentioned, GSHA outputs the elevation or the water depth as well as the flow rate for each stream node. And so you can view those water depths. This is Google Earth. You can view those in Google Earth or in WMS. I'm not sure that I have this video, so I guess that's not going to work. So let me do this slide. This one.
After the outlet, after and this flat area, what the output what we can get? Those. Columns indicates, I think, the water depth.
Yeah, water depth.
Okay. After just the outlet of the watershed, it doesn't give any values. مش المية جاية. Okay.
You're wondering how to get the water depth at the outlet?
I'm wondering what are the outputs here? No. Calculated.
Yeah, that's not part of the model. You mean down here?
Yes.
That would you'd have to do a model for that area. So the model for this it covers this area, this mountainous area. You could include this part of the watershed in your model if you wanted, but it's not part of this particular model. Okay, so the next thing we're going to talk about. So I'm going to talk about several topics, and then I'm going to do a little demonstration on how to do some of this stuff. So I want to talk about index maps. So when you set up your GSSHA model, one important part of your GSSHA model is something called an index map. And an index map is just an integer value, so a number like 1, 2, 3, 4, 5, just a whole number that is assigned to each cell on your grid. So this is what an index map looks like. And they're stored in WMS as just integers. Okay? And we're going to talk about how to create index maps. So the way you create index maps is just like kind of like how you create curve numbers. You define your land use layer, your soil type layer, and then usually you'll combine the land use and soil type into a combined layer, and then you can define parameters for each of those layers. So you have your GSSHA model, you have a soils layer, you have your land use layer, and then you can combine those layers or you can create index maps from those different layers. And I've already shown you how you kind of create an index map, but I'll do a demonstration and show you some more. So there's a table. So once you create these index maps, then you have to define infiltration values and roughness values for each of these index map values. The roughness values, there are several locations to get the roughness values. And what I do, I usually just search for roughness table, Manning's roughness table, something like that. And it'll come up with some website that has Manning's roughness values. And there will be a table on that website you could use. Usually for overland flow, the roughness values are going to be higher than what are in this table because these roughness values are for channel flow, and you'll have to multiply the values by 2 or something like that, just so to get a starting value for Manning's roughness. For green and Ampt parameters, I can go to GSSHAWiki.com, green and Ampt. Green and Ampt method is the method that GSSHA uses for infiltration, so for the soil going into the soil, for the water going into the soil. And this table on the GSSHA wiki is what you'll use to get the parameters. So use this table right here. If your soil type, like Dr. Mon was mentioning, you have sandstone in some areas and things like that. If you have a soil type that's not in this table, then you'll just have to get the closest soil type that's in this table. So maybe sandstone would be kind of like clay. There probably isn't very much infiltration into sandstone, and so you could maybe use the clay values, but some of the values might not be appropriate because for example, you're not going to have any your bubbling pressure geometric mean. You're probably not going to have any capillary pressure in sandstone, and so you'd probably enter a really low value for that, but you'll have to estimate the values if you have something that's not in this table. Okay? So you have to enter those values, and then there are different places you can get soil and land use data. We've already talked about all this stuff about getting soil and land use data, and a lot of it you can just get in WMS. If there's an area where you don't have any soil or land use data, you'll just have to create soil or land use polygons in a soil land use coverage and get that data. In the US, they have soil databases, different soil databases, and that's what this is talking about, how to use those soil databases. There's something called Surgo data, and Surgo, you actually don't need to do this anymore. I probably need to change the slide, but you can join layers between database files. That's what all that stuff is. So your land use represents how well water is retained on the land surface until it can transpire, evaporate, or infiltrate. So a lot of times land use is going to be used for infiltration parameters as well as evapotranspiration parameters. So evaporation or transpiration. And there are different models that GSSHA uses for that. So there are textbook values that are used for roughness that are based on land cover, and that's why I said you go online, you can find tabular values. And also WMS, in the WMS files there's a CMT, which is a channel mapping table file. That's a GSSHA file that you can read in that has different roughness values for different land use types. And you could read that in, or you could just define the roughness values and get that data. This talks about getting land use data off the internet. I'm not going to cover that. And so to create your index maps, first of all, you read your land use and soil shape files. Then you don't really need, if you have to do this joining tables, you usually won't need to do that. But if you have to, you can do that. You convert your land use and soil shape files to polygons in the map module. Create your index maps, and then you define your mapping table parameters. This is how you define your parameters at each cell in your 2D grid in your model. So the way you define parameters in GSSHA for each cell is you define these index maps that represent your land use or soil type, and then for each index map ID you define roughness values or infiltration parameters or whatever else you need to use in GSSHA. So that's how you define your parameters for GSSHA. I'm not going to do a demonstration yet. We have another thing to talk about. So GSHA uses a model called the Green and Ampt infiltration model. And we've already talked about a lot of this stuff, but basically the way this works is you define all of your parameters using the data that's on the GSHA wiki. So this table here, these are your Green and Ampt parameters that you're going to use. And these parameters were taken from a study done by this guy named Rawls, who published a paper in 1983, and we took the values from his paper. And you can calibrate these values if you're not sure that these values are correct for your area. You can run a calibration in GSHA if you have calibration data. So we've already talked about how to set up infiltration. You define your index maps, then define your infiltration parameters using that table. And normally there are two sets of infiltration parameters that you need to define in WMS. Somebody have the dongle? I just want to... Could somebody pass it up here? Just throw it. I should have one, but I don't. Well, the thing is, I thought my computer would work, but so I'm using this computer. It's on. I do have a license on my computer, but okay. So let's look at WMS here really quick. So normally the way you would define your mapping tables is you define both your index maps. You usually would define a land use index map, a soil type index map, and then a combined land use and soil type index map. The combined index map is used for your GSHA Green and Ampt parameters. So your infiltration parameters are going to use the combined index map, because the infiltration parameters depend on both your land use and your soil type. So if I have like a paved area, but my soil type is maybe clay, or if it's sandy soil, but it's paved, I don't have very much infiltration. But if I have the same soil type, just it's in a rural area where there's no pavement or anything like that, then my infiltration is going to be much different. And so you need to combine your land use and soil type. And I'll demonstrate that here later, but the other thing is, let's see if I have a GSHA model I can read. So here's my GSHA model. If I go to the map tables, so you have to, for infiltration, you have to define both infiltration parameters, and that's just these values here. You also have to define an initial moisture value. And the initial moisture, usually it may or may not depend on the land use. So what I usually do is I just define this based on my soil type for my initial moisture. But it could depend on the land use too. And so this is just the initial moisture that you're assuming is in all of your soils. So once you define those things, you define your combined index map and your soil type and land use index maps, and then you define these mapping table properties for the different combinations of land use and soil type. This is your table that you use, and this is just the same thing that's on the GSHA wiki. you define your initial conditions. So this is the initial moisture values. And you need to make sure green and Ampt is turned on. Then you can run your model, visualize the results, and that's how you do that. The other thing I want to talk about is different scenarios. So a lot of times you might want to simulate land use changes in a watershed. So maybe I have a development that I'm planning, something like that. I can simulate land use changes. And that's called scenario modeling. The WMS interface to GSHA allows you to do different scenarios. So I can have one scenario that's maybe pre-development conditions, and then another scenario that's post-development conditions. And the way I define those scenarios is just making sure I'm recording. I forgot whether I was recording. The way I define those scenarios is by creating a new GSHA scenario. There's an option to create a new scenario. And one thing though is I have to use the same grid for all my different scenarios. I can only have one grid in WMS, but I can have several different scenarios associated with that grid. And there's a workshop that you have that talks about how to do scenario modeling. So I might kind of demonstrate this, how this is done. And so these are the rules you follow to create a new scenario. I don't know that I'm going to cover all these rules, but usually what you would do is you have a GSHA coverage, you duplicate the GSHA coverage, you would duplicate your project, and then you would assign a new coverage to your duplicate project. And it's probably best if I just demonstrate how you do this. So this is what several scenarios look like. I can have several GSHA coverages right here, and then down here I have several different scenarios. So maybe I have a scenario that is just my original scenario, and then I try adding a detention basin to that. So that's this scenario. Then I have another scenario that's my new land use, I guess, down here. This is my base scenario. And then I try adding a wetland. So I have these 4 different scenarios, and then I can run all these scenarios together. They're on the same grid, but I have just different scenarios, different coverages, GSHA coverages. And I'll show you, maybe I'll show you how to do different scenarios. So this, I'm not going to do all this. I'll just demonstrate it, how that's done. That'll be the easiest way to show you. Okay, then finally I want to talk about some advanced topics in GSHA. So with GSHA, these are some of the advanced things you can do in GSHA. You can model embankments and hydraulic structures, reservoirs and lakes. You can do long-term simulations. You can do groundwater modeling, wetland modeling, sediment transport and contaminant transport, and storm and tile drain modeling. And so let's talk about some of those things. So an embankment is just an embankment, where the earth's surface is higher in some location. So do you use that term, embankments?
Yeah.
You know about that?
Embankments usually are dams built along the side of the river.
Yeah.
Yes, we know that term, but what we are using here is detention dams.
Okay.
This is what we are working in. So
Okay.
maybe if you can give us an example.
So we can talk about detention basins. So You define an embankment in GSSHA using the Create Arc tool. And you just create an arc that represents your embankment, and then you define elevations along that arc. And so this line, for example, this red line represents an embankment in WMS. And I can use it to represent culverts. So here I have a culvert that's on my stream, and I can define the culvert parameters in GSSHA, well, in WMS, and then it saves that out to GSSHA. I could also use embankments to represent lake embankments or reservoir detention basin embankments, like you were mentioning. This is how you set up reservoirs in WMS. First, you create generic arcs that represent your lake boundary. Actually, this is not correct. So I'll show you, I'm going to show you how to define a lake in WMS. We'll do that later. To define an embankment, you create an embankment arc downstream from your lake, and that represents the reservoir embankment. And then you have to define your elevations along that embankment. And I'm going to skip some. Some of these are older slides, so we don't do lakes like that anymore. It used to be how we did them. And I'll show you how to do lakes. One of the things, whenever you do a lake, you have to define outflow properties. So you have to define any outlet structures like culverts, weirs, rating curves, or scheduled discharges. So rating curve is depth, outflow versus depth, or you could find discharges at different times. And that's in this window. This window allows you to define all those things. I'll show you how you do that. When you define long-term simulations in GSSHA, GSSHA can be run for any amount of time, so you can run it for as long as you want. The longer you run, the longer it's going to take to run your simulation. And any number of storm events can be run. And GSSHA runs evapotranspiration and soil moisture accounting. So the method that we talked about yesterday that's used in HMS, that same method is used in GSSHA between the storm events. And WMS just has some default parameters that are written to that method. GSSHA has some default parameters that are used in that method. If you have groundwater turned on, groundwater modeling, it does groundwater modeling for the long-term simulation. And that's about all I wanted to say with that. For long-term simulation, you have to turn on this option in the job control dialog, the long-term simulation option. And then you go to edit the long-term simulation parameters, and it comes up with this window. In this window, you have to define something called an HMET file. It stands for hydrometeorologic file, data file. And there are 3 different formats. The GSSHA wiki will have the information on those formats. Basically what it is, it's your temperature, dew point, and radiation. If you have that information, you don't need the radiation because GSSHA will compute the radiation depending on your latitude and longitude. So right here, GSSHA computes the radiation. But if you have the radiation, you can include that in your file. And so there's a bunch of parameters that you need to do a long-term simulation. And you also have to define your evapotranspiration. So this is a sample table of the parameters that you would define for evapotranspiration. And that's usually dependent on your land use. It could also be dependent on your soil type, but usually your land use. And then you get long-term simulation results, and you can have observed versus calibrated data. You can calibrate long-term simulations also, just like you can calibrate short-term simulations in GSSHA. GSSHA also has does groundwater flow, and this is the equation that's used for groundwater flow. It's just the two-dimensional groundwater flow equation in two directions. And the surface water and groundwater both interact. So like that slide I showed you earlier today, when you have groundwater that's above your channel water surface elevation, then that groundwater goes into your channel. If the channel is above the groundwater, then the water from the groundwater will not go into your channel. And usually it's just a one-way. GSHA models it as a one-way from your groundwater into your channel, not from your channel into your groundwater. To do groundwater simulation, you have to turn on this option in the job control to do your groundwater. And then you define your groundwater parameters. The most important groundwater parameters that you have to define are your aquifer bottom and your water table. And those are just maps, so continuous data sets that are assigned to your 2D grid. And then you also have to define some mapping table parameters. And the parameters you have to define are your hydraulic conductivity and your porosity for your different index mapped values. If you do all that, and also you might want to define some groundwater boundary conditions. WMS will automatically define some boundary conditions, like wherever there's a stream in WMS, then WMS will define that as a river boundary condition. So something like this. So wherever there's a stream, it'll be a river. Everywhere else is just going to be a generic boundary condition unless you define it some other way. So this slide just shows you the effects of groundwater on your model. Your upstream gauge, you have the yellow line represents the flow without groundwater. The black line represents the flow with groundwater. And so groundwater has some effect on the flow rate out of your watershed, and it has some effect on the base flow out of your watershed. And then same thing down here. So this plot shows you the blue line represents flow without groundwater. The red or pink colored line represents flow with groundwater. So the peaks are going to go down if you're simulating groundwater, and then the base flow is going to go up. You can also model wetlands in WMS, or in WMS and GSHA. And wetlands are just places that are wet. And these are the parameters you have to define for wetlands. The way you model wetlands is you define a polygon that represents that wetland, and then for that polygon you define the parameters, these parameters for that polygon. So the initial storage in the wetland, the retention depth, and just all these parameters. And for more information on these parameters, you can get more information from the GSHA wiki. You can also do storm and tile drain modeling in GSHA. And okay, so this slide says we do not recommend using GSHA to set up a storm tile drain model right now, but now you can. Okay, so you can do storm and tile drain modeling in GSHA now. That was in 2009, but I should probably take that comment out. So it works now in GSHA, so you can do that. What's that?
We still have the comment in our.
So cross it out. Go to your slide and print it out or something and cross it out.
No, I will not use.
So let's demonstrate. I'm going to demonstrate some of these things I've been talking about. So let's just create a GSHA model. So I'm going to create a model for GSHA. I'll just use the hydrologic modeling wizard to do that. And we'll save it here. I'm going to call this demo. We'll define a projection. So the projection for my data is UTM zone 12. We're in Utah. And we'll define a project boundary. So the project boundary is Park City. It's the name of the area we're going to model. So here's Park City. This is in Utah, United States. And for this, so that's my project boundary. And I have a bunch of data for this area, so I'm just going to read in my data that I have. So I have a DEM, read in the DEM. So here's my DEM. I'll also read in some land use data. Here's my land use data. I also have some soils data. So there's, let's see. This is the soil data covering my watershed. And okay, so we're just going to read in all of that information. So I have land use, soils, elevation data. We're going to run Topaz, then we'll delineate the watershed. So the watershed I want to delineate is in this area. If I want, I can download an image for this area and you can look at it, but we're just going to delineate this watershed. And then we'll create a GSHA model for that. So there's my watershed. Create a GSHA model. I'll set my stream attribute. So this is my 1D hydraulic model. I'm going to define all these streams as trapezoidal. The Manning's roughness, it's the same. A depth. Bottom width, side slope. Okay, then I'm going to redistribute my vertices on those streams, and so this should be about the same as the cell size that I'm going to use in my model. I'm just going to redistribute to be 90 meters. And then I'm going to smooth my stream segments. So to smooth the stream segments, what you do is you select the streams along a certain line. So smooth streams, smooth these stream segments. I can look at this. One thing you could do is you can turn on adverse slopes, and I can see where I have problems with my streams. So my adverse slopes are actually turned on. I'm going to turn this off. We'll be able to look at the adverse slopes. So this stream here has an adverse slope, this stream does, and this stream does. And so I'm going to select those streams, select this button, and I'm just going to I can select some points I want to keep here. and just interpolate between those points. Okay, I can also select this button and interpolate my stream elevations. But these are the elevations I'm going to use. I'm going to keep.
We have selected the stream and defined it as trapezoidal.
Mm-hmm.
If we have the survey of many cross sections along the each stream,
Mm-hmm.
is there a possibility to define many cross sections
Yeah, you can define many cross sections.
with different?
So what you would do is you'd have to split your arc. If you have, so you're asking if you have several cross sections along along a stream segment, you'd have to split your arc. So you go to the map module, create a node here. Whoops. So you'd create a node, and then for each arc, you would define a different cross section. So you define a cross section channel, define a different cross section for each of those arcs. But let me make sure that's still defined. Okay, so I'm going to just finish cleaning up these streams. And this is just defining my 1D hydraulic model. Oops. Okay, so now I have no more adverse slopes on my streams. Okay, then I go and define my grid. So I'm going to use a 90-meter cell size. And so this is my grid. I'm going to define a simulation. Probably don't want to start in 1899. I'll start in 2015. We'll end in 2015. We'll start at 1-1, go to 1-3, let's say. Okay, so we have a 2-day simulation, set our job control data, and then we can create our coverages, so create our land use and soil type coverages. And I'm just using this wizard to do that. And then I can create my index maps. So I'm going to create my land use index map. Actually, let me move this out of the way so you can see what this does. Compute index maps. Create our land use index map. Call this land. So there's my land uses. We'll create our soil texture index map. Call that soil texture. So there's my soil textures. And then we'll create a combined index map. That's the combined land use and soil index map. So each land use and soil combination has a type. Then WMS brings up the map table editor, and this is where I define the parameters for each of those land use and soil combinations. So I need to define, whenever I do a GSSHA model, I have to have roughness values. So I'll select the land use index map for generating my roughness values. So these are the different land uses. If I have a name for the land uses, it will read in those names, but I don't have a name. You could enter, if you know what each of these land use IDs represent, you can enter a name here though. But I'm just gonna, let's assume we have the same roughness for all of these land use types, just for this demo. Okay, so those are all the same. Then I need to enter my infiltration parameters. So like I mentioned, WMS or GSSHA uses the green and Ampt infiltration method. So use this green and Ampt infiltration method, and then we'll use the combined index map and generate IDs using that combined index map. Some of these parameters WMS already has here. They may not be correct. I think for this project it's not correct. So I'm going to get these parameters from the table. So the way this works is I go to this table, and on this table I have loam as one of my soils. So I go here to loam, and then these are the parameters for loam. First parameter is hydraulic conductivity. So I go over here from loam, go to hydraulic conductivity. That's this value, 1.32. And it says multiply by 0.5 for GA methods. GA is green Ampt. So I need to multiply that by 0.5. So what is that? 1.32 divided by 0.5 times 0.5 is 0.6 whatever, 67 something. So we're going to enter 0.67 for loam. And then the next thing we need is capillary head. Capillary head is this value right here. Or actually it's this value, sorry. Wetting front suction head, capillary head. And for loam it's 8.89. So I'm going to take 8.89, I'm going to put that into here. Then I need my porosity. The porosity is, the effective porosity is what I want to use. And that is 0.434. You know about porosity?
Yes.
Okay. I need my pore distribution index. That is this right here, 0.252. Residual saturation, that's how much water is, kind of the minimum amount of water after soil's dried out. So for loam, that's the value. Field capacity, that's right here. Take this value. And wilting point is right here. Wilting point saturation. So I'll paste those values in. And I can do that for all of these different soil types. And the land uses are different. I could find different values for different land uses, whatever. So I'm just going to take these values. I'm going to use it for all my soil types just for the demonstration purposes.
If I have a table, it should be
Yeah, so there's this option down here to export this table, and I can save this out, and then once I've exported, I could read it back in. I can import a new table. So you don't have to go through all that work every time. Also, I need to define my initial moisture, and my initial moisture is usually based on just my soil type. And a good value for initial moisture is your field capacity. So the wilting point is kind of where plants are wilting. It depends on what area you're in. Maybe somewhere like Egypt, most of the time you're at the wilting point. But somewhere where the plants are growing and stuff, then you would maybe be more toward your field capacity. So I'm just going to use my field capacity for my initial moisture. And this has to be less than the porosity of the soil. So you can't have more initial moisture than your porosity. If it's greater than that, you're going to get an error when you run GSHA. It'll probably crash or something. So then I go back here The other thing I need to do is define my channel routing. So I'm going to select this diffusive wave option, and that will define channel 1D, my 1D hydraulic model. And that's the only option to use for that. There's some parameters I'm going to talk about here later. But you define that. Define your precipitation for this. I'm going to use a hyetograph, and we'll use one of these standard hyetographs. So let's do the type 2 24-hour storm, and we'll define a depth. The depth is for this storm is 59 millimeters. And then we'll clean up our model. No errors were found. We run clean dam, and we'll save this model. Call this WMS. We'll call it Park City. And we'll run the model. Okay, so let's let this model run, and we're going to take a break. Is it time for lunch? Do we know? It is time? Okay, so we're going to take a break for lunch, and then at 1:05 we'll start up again, and I'll finish showing you some of this demo. So did you have some questions? Uh-huh. Okay. Okay, I'll come and look at it. Any questions before we break for lunch?